in section 4.1, what we're going to talk about is one-to-one functions. And basically what that means is each x value has its own y value. So the idea is if you have two different x values, x1 and x2, they need to have two different y values. The only way that you should have the same y value for something is if you have the same x value. What does that mean? It means that we should have no two x values that are plugging in that get the same y value. Means that we should have no repeating y's. Now, we've seen something like this before when we talk about no repeating x's, and that was when something was not a function. This is something different. We're asking if a function's one-to-one, which means we want no repeating y's. It means each x should have its own y. If somehow you end up with the same y, it's got to be that the two x's were the same. So, we're going to have to look at making sure that y's do not repeat. So this first one that we're going to look at, this first function, and we're going to decide whether or not it's one-to-one, is y equals negative 5x plus 2. Well, basically, what is negative 5x plus 2? It's a line with a negative slope that goes through positive 2 on the y-axis and heads downward. Something like this, because it's got a negative slope. What do you know about lines? Each x value you plug in, you get a different y value because you have a slope. You'll have a rise over run that each time you're going to go to a different point. So is this function one-to-one? Absolutely. None of the y values will repeat. Each time I plug in an x, I'm going to get out a different y. However, let's take a look at b with the absolute value function. If I plug in negative 1, I'll get the absolute value of 2 times negative 1, which is negative 2 inside there. The absolute value of negative 2 would be a positive 2. However, if I plug in a positive 1, I will also get the absolute value of 2 times positive 1. Well, you'll do the 2 times 1, which is 2, and then the absolute value of 2 is also 2. The problem with this one is we plugged in two different y's, but we plugged in two different x's, but we got out the same y. What does that mean? It means it's not one-to-one. You have a repeating y. And the reason why that happens is if we remember, this is an absolute value graph. That's the V shape. Notice you'll always have 2 points where the y's are the same. So no, this is not going to be one-to-one. We will have repeating y values. If you're not sure, do what we did here and plug in some values. Now let's take a look at C. Let's try the same idea. Let's plug in 1. Well, if you plug in 1, you'll get 100 minus 1 squared. Well, 1 squared is just 1. So you get 100 minus 1, which is 99, so you get the square root of 99. Now let's do the same thing, but plug in a negative 1. Well, negative 1 squared is still a positive 1. So you'll still get 100 minus 1, which is, again, going to give you the square root of 99. What's the problem again? Is notice we've got two different x values, but we're getting out the same exact y value. It's not pretty, but they're both getting out the square root of 99. And that's not okay. So this is not going to be one-to-one. Why? Because you've got repeating y's. So that is not going to be one-to-one. If you remember back when we talked about the x is not repeating, and whether or not something's a function, we came up with something called the vertical line test. So if a vertical line hit the graph more than once, it was not a function because you repeated your x values. If somehow your vertical lines only hit once at most, then it was a function because that would mean that your x values would not be repeating. So the kind of alignment here is we're worried about y values, So this time, instead of a vertical line test, we're going to be talking about a horizontal line test. So the horizontal line test that we're going to look at is going to tell us whether or not something is one-to-one. If a horizontal line only touches it at most once, it is one-to-one. If a horizontal line hits it more than once, it cannot be one-to-one. And we'll worry about why we even care about one-to-one later, one thing at a time. So this first one, we've got on problem A, on this first set of examples, we've got a line. And the horizontal lines, any of them, will only hit the graph once. Which means, because it does pass the horizontal line test, that yes, it will be one-to-one. However, let's look at B's parabola. Notice B's parabola is you will have many horizontal lines that hit it more than once. So that means it's going to fail the horizontal line test, which means no, it is not one-to-one. Let's take a look at C. In C, we'll try our horizontal line test to see if it's one-to-one, drawing a bunch of horizontal lines. What we notice is none of them will hit the graph more than once. So yes, it will be one-to-one. Okay, in D, we've got, notice, an x squared graph, which means we've got a parabola. With a minus sign means it's pointed downward. So it'll look something like this, which means, is this graph going to be one-to-one? No, because it won't pass the vertical line test, because a vertical line will pass through it more than once. So no, it is not one-to-one. The next one, we've got something a little different. What shape do we have? We have an x cubed graph, which is that snake graph going upwards. And notice, what we notice is if we do our horizontal line test, is the horizontal lines will hit it at most once. So yes, this will be one-to-one. Now the last one that you might not remember from college algebra is this 1 over x plus 2. And remembering that because its denominator is 0 at x equals -2, that's going to be your vertical asymptote at -2. You also, because the bottom is bigger, you learn this, has a bigger degree in college algebra, you learn this, is that you will have a horizontal asymptote at 0. And you get a graph that looks something like this because it will alternate between being positive and being negative. But what you'll notice is a graph like this is the same idea, is it will, if we do the horizontal line test, horizontal lines will only hit it once. So, is it a one-to-one? Yes. If you weren't sure, what you could do is plug in some values, and what you'd notice is each time you get out a different y value, which means that you wouldn't be repeating yourself, which means, yes, it would be one-to-one. So next comes the punchline. Why do we care if something is one-to-one? We care if a graph is one-to-one because that's when we're going to know that it has an inverse. So, a function is one-to-one if it has an inverse. So we'll call that 1-to-1. Also, if it's one-to-one, it's also going to pass the horizontal line test. So the way that I think about this is I think about a bunch of different ideas being interchangeable. So the way that I would kind of view this if I were you is I'd say, okay, just kind of group all of these things together. Is that passing the horizontal line test means that I'll be one-to-one, but it means I will also have an inverse. And all of those things can be used interchangeably, that they mean the same thing. If you pass the horizontal line test, you're one-to-one and have an inverse. If you have an inverse, it's because you're one-to-one and you pass the horizontal line test. You can use all of those terms interchangeably. The question is why? Well, it has to do with because of the way inverses work. inverses basically undo what your function was doing. So if an original function, like this one, f of x equals 2x, so if you plug in 1 to your function, you get out the value 2. Because you'll do 2 times 1 is 2. So what does the inverse do? The inverse says, I'm going to do the reverse. I'm going to take my 2 and undo what you just did and send it back to 1. So what this means is if the original function has the point 1, 2, the inverse has to have the reverse, has to undo that and send 2 back to 1. Just to give you another example. So this function 2x, if I plug in 2, gives us out 4. That's what the original function does. So the original function, if we plug in 2, we get out 4. That means that its inverse would have to do the reverse, would have to plug in, if you plug in 4, would give us back 2. It would undo the function. So that's kind of the idea. So what is kind of an easier way to put this? Your original function, f, takes x's and plugs them in and gets out a y. Your inverse is going to take whatever you got back out and plug it back in and turn it back into an x. And because it undoes the function f, what we want to do is basically say it's the inverse of f. So we did this. We came up with new notation, which is to call f with a little minus 1. And the little minus 1 stands for inverse. It's not an exponent. That little minus 1 means an inverse. Of what? Well, whatever letter you've got, so it means the inverse of f. So what we've noticed is that if an original function has an x comma y in it, the inverse will have the reverse, y comma x. So basically, what are you doing? Your inverse swaps your x's and your y's. So for inverses, we swap x's and y's. It's a quick way to kind of look at it. Why would we want to look at it this way? Well, what this means is if our original function passes the horizontal line test, which is a y test, that means when we go to look at our inverse, well, remember the inverse has us swapping our x's and our y's. Our inverse has us swapping our x's and our y's. That means instead of passing the horizontal line test, the inverse would have to pass we'd swap out the y here for an x, we'd have to pass the vertical line test. What does that mean? It means that it would be a function. So by making sure that the original function passes the horizontal line test, when we swap the x's and y's for the inverse, that makes sure that the inverse passes the vertical line test so that it is a function. So, by making sure something passes the horizontal line test, we're making sure that when we swap our x's and y's, we'll actually still have a function when we're all said and done with it. That's why we do this.